Hello BC Calculus students, this is Mr. Johnson and this is the start of section 8.3, and in this section we're going to tackle a number of the convergence tests. But first, let's take a look at the 4 warm-up problems. We're on page 38, and if you are feeling really confident with this stuff, you can pause and just try these on your own. This isn't any new information, this is just information from section 8.1 and 8.3. And if not, you can walk through it with me right now or just check your work later, but I'm just going to show you the first 4 problems in this first video. So our task is to determine whether each of these series is either convergent or divergent. And if it's convergent, we're going to try to find the sum if we can. So this first one is going to appear to us to be a geometric series, and we have a as the first term, which is 4. And then remember, r is going to be what you multiply each of the terms by that common ratio, which is going to be 2/5. If you ever struggle with knowing what r is, I mentioned this in a previous video, but you could always take any of the terms and divide by the previous term. And the key here is that you want to make sure that you do this consistently term to term. So don't just stop as you consider the first term, the second term divided by the first term. Make sure that, if you multiply the next term, it would be a common ratio of 2/5, and then the next term and so on. Just make sure that you're not rushing too much through that process. So our r value is 2/5, and remember the absolute value of r must be less than 1 for the geometric series to converge, and this obviously is. So what we're going to do is find the sum, and the sum is the formula a over 1 minus r, which is going to be 4 divided by 1 minus 2/5, and we're going to multiply by 5 and by 5, and so we get 20 over 5 minus 2, and so our answer here is that this particular series converges to the sum of 20 over 3. So there's a good example of a geometric series. For number 2, we have another geometric series, although we have 2 separate ones. Keep in mind that the r value here is 1/10, and that's a convergent r value. So again, that's in between -1 and 1. And then this r value here is going to be 2/10, and that of course also fits into the category of a convergent geometric series. So what I'm going to do is split these up, because we can do this using our properties of series. In fact, I'm going to take the 2 and pull it to the front of this first one, so that I have the geometric series with an r value of 1/10 and an a value of 1/10. Now keep in mind, and I just wanted to show you this strategy, this 2 here I'm going to multiply it later on in the end. Okay, so what I have is a sum of 1 over 10 divided by 1 minus 1 over 10, and we multiply to clear our fractions. And so we get 1 divided by 10 minus 1, which is, of course, 1/9. Now, I am going to multiply that by 2, because remember, I have this 2 that I moved to the outside of the series. So I'm going to apply that in the end. Let's go ahead and work on the second one, however, really quick. So we have n is 1 to infinity of 2/10 to the n. Of course, r is 2/10, and a happens to also be 2/10, the first term. So the sum is 2/10 divided by 1 minus 2/10. So we multiply by 10, and we get 2 divided by 10 minus 2, which is 2 over 8, which is 1/4. Okay, so here's what we have. Let's put all of this together really quickly. So we have 2 that's multiplied by the sum of 1/9 plus 1/4, and let's just work on these fractions a little bit. So we have 2/9 plus 1/4, which is the same thing as 8 over 36. Don't forget that easy math you learned way back when. So common denominator, now we can add up our fractions, and we get 17 over 36. So we would say that this series is convergent to 17 over 36. So that's another example of a geometric series. Right now, that's probably the most common one that we've learned. Okay, let's try to tackle question 3. So question 3, we start to think through our options here. Remember the very first test that we had, test number 1, was the nth term test. And the nth term test basically is the limit test, where you, sorry, I'm going to write that down, where you take the limit as n goes to infinity of the series generator. We could have done this in the previous 2 series, although we would have gotten 0, so it would have given us no information that was helpful. But in this case, we get a limit of 1/3. Since that limit is not 0, what that means, just remember the purpose behind this test. If we were to list out the first term and then add the second term and then add the third term and the fourth term and so on for a very, very, very long period of time, the nth term test, the limit test, allows us to identify what the nth term is going to as n goes to infinity, which in this case is going to be 1/3. So really what we're doing, in essence, is that we're adding 1/3 forever, which means that we will continue to add, we will continue to diverge as a series. So this particular series is divergent by the nth term test. All right, our last example. And this is a really good one. We've talked about this before in section 8.2 when we talked about partial sums. So this problem specifies that we have a partial sum that we're analyzing. And in this problem, we're looking for the infinite series k goes from 1 to infinity of a sub k. So in other words, we don't really know what this particular series is. We don't know the generator, but what we have is the nth partial sum formula. Now the problem is asking us for the sum of this particular series, and keep in mind that this series may diverge. That is one of our options here. But we're looking for the sum of a series. Now remember, we don't actually have the particular terms written out explicitly for us. So what I'm going to try to do, just to give you a sense of what we're actually trying to accomplish here, is that the first partial sum is simply a sub 1. The second partial sum is a sub 1 plus a sub 2. The third partial sum is a sub 1 plus a sub 2 plus a sub 3. Now, I will stop there for just a moment. So if we were to use our formula that they give in the problem, if we have the first partial sum, that means that n is 1, and if I substitute n is equal to 1, I get 1 over 3 plus 1, which is simply just 1/4. Okay, if n is, for the second partial sum, if n is 2, I get 2 divided by 3 times 2, which is 6 plus 1, which is 2/7. If we're looking for the third partial sum, n is 3, I get 3 divided by 3 times 3 is 9 plus 1, so I get 3 over 10. Okay, now, what are we really doing here? Well, the partial sums are made up of these mini series. So for example, if you were to look at the 10th partial sum, you'd have a sub 1 plus a sub 2 plus a sub 3 and so on to a sub 10. And that gives us a partial sum of 10 divided by 10 times 3, which is 30 plus 1, so 31. Now the question is, what are we getting closer and closer to? So if we were to look at the 100th partial sum, where you have 100 of these added up, versus the millionth, versus the whatever, what are we getting closer and closer to? Well, let's just say we have the nth partial sum. That's going to be a sub 1 plus a sub 2 plus a sub 3 and so on until we get to a sub n. Now if we let n go to infinity and we analyze the formula for our partial sums, we get 1/3. What this means is that if we took the partial sum, the nth partial sum, and we get 1/3 for that value, the theorem that we studied in section 8.2 when we talked about partial sums says that if the limit of the nth partial sum as n goes to infinity is equal to, I believe they used L, it doesn't really matter here, but if it gives you a value, then the particular series that we're dealing with is going to sum up to that value of the limit of the partial sum. So in other words, for this particular problem, the series that we're looking at here, a sub k, where k goes from 1 to infinity, has a sum of 1/3 simply because the nth partial sum has a limit as n goes to infinity of 1/3. Now, if that particular limit did not exist, let's say that limit goes to infinity, well, then that would imply that the series would then go to infinity and would be divergent. So the partial sums are a way for us to look at what a series is going to do in the long run. All right, I hope that's helpful. That's the warm-up for 8.3. We will now dive into, in the next video, some of the convergence tests.